Good day everyone, my name is Alger, and in this video we are going to solve the following given problems using uh, Grasp software. So it's actually a software that we can use to solve the following problems, given that these problems are two-dimensional structures. So, and first we're going to solve the problem A, which is a beam that has a rectangular cross-section of 250 by 400 millimeters, and with its assumed material properties, with its modulus of elasticity that is 21 kilonewton per square millimeters, its unit weight is 24 kilonewton per cubic meters, and the coefficient of thermal expansion is 12 times 10 raised to negative 6. And so this will be our figure, our basis for doing, or this is actually the structure. And then we are going to determine the reactions at A, the vertical and the moment. So basically there's only a reaction along y-axis, because the reactions at x-axis is going to be 0 from here. So that's our preliminary investigation on the structure. And the shear and moment at the left end in BC, and also the maximum bending moment in BC, in member BC. So let's go.
So this is our Grasp software, and we're in its window. And so before plotting the structure, the given structure, the beam, we have to first define the unit. So we have observed from the given, it's on a system international units. So we're going to set them and click OK. And then for my own convenience, I want to show the grid lines, in order for me to have a proper basis, or for me to be guided in plotting the structure. No? So I'm gonna zoom it out. So now I am ready to put the nodes. No? The nodes. So here, this is going to be my reference point. So this will be the node 1, and then I just have to count from the given. That's 12 meters. The first number: 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, and 12, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 again, and then 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so given that we've already applied the node, so before putting the members, I just have to, set the materials, and we're just gonna have to add the materials. So from our given, I'm gonna name this materials or concrete. From the given, we have a given modulus of elasticity that is 21 kilonewton per millimeter squared. As you can see here, its units is supposed to be newton per millimeter squared. So 21 kilonewton is supposed to be 21,000 newton per millimeter squared, and our unit weight that is 24. And our coefficient of thermal expansion that is 12 times 10 raised to the negative 6, and that would be 0.000012. Then we click OK. Now close, and then yes, and so we are ready to put our members. So we just have to long press the left click. Now we can add the members, just like that, and then we add the supports. So here are the supports. Just click on the first node, that's supposed to be our point A. Then we click this fixed support. It's actually fixed. You can see here the properties, or the parameters will be fixed. Then we click OK. Then it will show, that the support at this point, at this node, is fixed. And so on the other side as well, that's fixed. And the distance from the first point of the point A from the diagram to that's 12 meters. That is a roller type of support. So we click this and okay. So we have applied the support, and then we will define the rectangular cross-section properties of the beams. So I just click it here. Given that our rectangular cross-section is 250 by 400 millimeters, so all dimensions are mm, so this is correct. Just need to edit this, and then okay. Then put this and see. Okay, Okay. Actually, yeah, for much more convenience, you can define first the cross-sectional member of a material, no? Then you can use check this use the sectional materials as default for new members to be added, so that uh, when you spontaneously continuously add new members, the member cross-section will be the same. Okay, so and then we add this. In this case, I have not set yet. I haven't set first the cross-sectional properties of the material or the member, so I have to do it manually for each member that I have added a while ago. So that's 250 and 400. That's 400, and that's okay. And so for this, we are going to add the the applied loading. So in our given problem, there are two types of loadings that is applied in the structure, and the specific members of the structure. Those are the distributed loads and the point loads. So for the distributed load, that is 20 kilonewton per meter. So we're gonna add load that is 20 kilonewton. So as you can see, I actually tap my cursor here, which means that I want to add a load at this member, with a specific length. A member letter is 12 meters. So we just have to click OK, and then we can see that distributed load is added to this member. And now let's apply a point load that is 250 kilonewton. In the same manner, we just have to choose a type of loading. So we choose this as 250. Then that member has a length of 4 meters. We're going to divide it by 2, since the point where the point load is applied is in the middle of that span length, that is 8 meters. So that would be 4 meters. Then we're gonna add it, and we click OK, and then there we see the applied loadings, the point loads and the distributed load. So then we have plotted the structure before. Then what we have to do now is run an analysis. Before that, we are going to remove the unused nodes. As you can see, if there are nodes that have been putted and have actually no connection with the structure, so they will be removed. And so, performing an analysis, you just have to click the perform the analysis, and we have to save the data file before conducting an analysis. And so let's name this A, problem A, prob A underscore A. So save, and then analysis will begin. You can see from here, what we're actually going to identify is the reactions at A. So the reactions at A, I'm gonna remove the grid, and I'm gonna show the grid as dots and not as lines for more convenience of viewing. So I'm gonna zoom it in for a much bigger view. So our reactions at A, that is a vertical reaction going downward, that's 55 to 25 kilonewtons, and our moment at Z, that is 221 kilonewton per that meter, kilonewton meters. And after that, we are going to identify the shear and moment at the left side and the left edited and member BC. So this is our member B and C. So view the results. Sorry. View the results. The shear and moment. So we're going to view the shear and moments. This is the member BC. This is actually the member BC. So I'm gonna tap here. This is the left end will be at point B. So this is going to be the left end, and this will be the right end. I'm gonna tap this member, and then it will show me the values of the shear and moment at that member. So since we're talking about identifying the shear and moment at the left end in the member BC, so this will be our Um, this will be our shear and moment values. The shear at the left end BC, that is 185.63 kilonewton, and the moment that is negative 442 kilonewton meters. We're going to close this, and then we will proceed with identifying the maximum bending moment in member BC. So in identifying the maximum bending moment, we are going to show the bending moment diagram. If you are going to evaluate the diagram as portrayed, we can see that at this point is the maximum value for the moment, no, positive moment. So let's assume that this in the member BC, this member actually is where the maximum moment is located. So I'm gonna tap this member to show the values for the moment, no, for the moment, and to locate its and to have its location. And we are going to evaluate where the actually in the analysis it is when the shear of the structure is going to is 0. That is when the there's of course the maximum moment. So here, as we can observe in the shear diagram portrayed that this it approaches from these values 5.63, negative 6.37. It is when the shear values passes through 0. So clearly we can say that we're going to identify that it is when the maximum moment of force, or at this point and at this location. So we can say that the maximum moment at the member BC is 418.670, and it is located at the 9 meters from 9 meters from point B. So that's it. Thank you for listening. I hope you learned some